Welcome back. So, as I've been thinking over the way that we've been handling binding problems and states and weights more generally, I realize that I've moved back and forth between a statistical mechanical description in which we wrote states and their corresponding weights, for example, in this language. And so this is the stat mech language. And a second and probably more transparent and maybe just a little bit more streamlined version in which I write uh, L divided by KD, where L is the concentration. And, a lot of the things that I do, I have to say probably come from a certain element of laziness. And, just to give you a sense of how and why that might be, let me just show you, the result of the last few hours of calculations. And I say this mainly because it's a mess, really, and it's kind of a horrid mess. And I just keep on trying to find ways to simplify my notation and not get confused and so on. And so that leads to the invention of little shortcuts notationally. And so in the context of these states and weights, I find this version much more notationally sympathetic, even though I find this one far more conceptually sympathetic. What I mean by that is that if I want to talk about or think about conceptually states and weights and binding, I will almost always use this version. And the reason is that it's a lot, for me, at least for me, it's a lot easier to move off into the unknown. And what I mean by that is, like, if I have a problem in which there's 3 ligand binding sites and so on, I don't really know how to do that in the KD language. I just don't, I'm not clever enough to figure it out. So I would use this language. But in terms of writing down states and weights and trying to be fast about it, this is the way that I would go at it. And so I want to just try and give you an indication of where these two worldviews come from and how they unite. To do that, I want to go back to our little vignette on cooperative binding. And I just want to let me remind you of what the essence of this was. So we had a receptor, which I show you here. And it's a receptor that had 2 binding sites. That's immaterial to the thing that I'm going to tell you now, but this is a good example because of the notational mess. And I'm going to show you all of the sort of labor-saving devices that I took, not because they're intellectually weighty, but because they were helpful just to make the notation more compact. And then there were 4 states. So the empty state of the double receptor, the singly occupied left, the singly occupied right, and then the doubly occupied. So those are my 4 states of occupancy. And being pedantic, I wrote down the energies, and they were of the form L epsilon solution. So that's just being really explicit and saying every ligand has an energy epsilon solution. And then I, systematically said, well, if one of them goes out of solution and is bound, then there's going to be L minus 1 epsilon solution plus epsilon B, and so on and so forth. Then what I said is, well, it would be a nice labor-saving device, and it would be simplicity if I were to choose this guy as my zero of energy. And I hope you will understand and agree that really it's energy differences that matter. And so the fact that I decided to choose this to be 0 is, again, immaterial, because at the end of the day, the energy of the bound state, this one, still has the same difference that it does in this new system that it did in the old. In other words, if you compare this energy, the L epsilon solution, compare this one to this one, and if you compute their difference, you'll find that it's this. So in other words, I haven't done anything really by carrying that out. So then I also noted that I am always free to multiply multiplicities by any factor I want. Like, let's say that you're in some room right now. Let's imagine that it's a classroom, and you want to know the probability that if you pick a person at random that they'll be bald. Okay. And the way that you would do that is you would count up the number of bald people, and you count up the number of not bald people, and the probability of bald is number of bald over number of bald plus number of not bald. Okay, but I could multiply the number of bald by 16 and the number of not bald by 16, and I will still get the same probabilities. Said differently, I can always multiply a statistical weight by all of them by the same factor, and it won't change anything. And so I elected to multiply by this factor on the grounds that what it would do is it would cancel off this thing, and I'd be left with statistical weight 1 for at least one of the states. And so again, this was a simplification done. It was really born of, not by necessity, but born of laziness, and born of elegance. This is a really nice looking result, and given that choice, then what we find is that the statistical weights collapse into this simple form. Well, maybe I should first say that the multiplicities become these guys. So L over omega, and hence the statistical weights become of this form. And that's the statistical mechanical thing that I started with up here. So I've now told you how we recover that statistical mechanical version. Now the reconciliation of these two worldviews is actually very simple, because if I take L over omega, e to the minus beta delta epsilon, and then I multiply it by little v over little v, where this is the volume of one lattice site. Now I can rewrite this as L over omega v times 1 over little v, and then e to the beta delta epsilon. This is also downstairs. This thing is v tot. And so if I have L over v tot, that's the concentration of L. So that gives me the L upstairs. And then downstairs I have Kd, where Kd is defined as 1 over little v, e to the beta delta epsilon. This is a reference concentration. And if you go look in your biochemistry books, you will see that there is a reference concentration. In general, it is 1 molar. Generally, L0, which is 1 over little v, according to me, is 1 molar, which corresponds to 10 to the ninth it corresponds to 10 to the ninth per micron cubed, or 1 per nanometer cubed. That's what the standard state concentration corresponds to. So what have I told you? What was the point of this whole little exercise? It's just to say that I'm going to freely pass back and forth between these two worldviews, and whenever I see this, I'm going to permit myself to always rewrite it as L over Kd. Okay, so that's this. So that was the point of this this little vignette, just to just really make sure that I drive home the idea of the equivalence of the statistical mechanical and the thermodynamic points of view. Although, we should remember the very interesting point made in Feynman's Nobel Prize speech, where he noted that that there's a psychological inequivalence. Even though two different methods that give the same answer, they're equivalent in that sense, they may be inequivalent when you launch into the unknown. And indeed, for me, that's for sure the case, where I find the statistical mechanical point of view much more useful for launching into the unknown than I find the thermodynamic one. That's me. It's subjective. There may be somebody that listens to this that will say, no, that's wrong. I don't do it that way. Well, just because you don't do it that way doesn't make it wrong that somebody else does it a different way. And that applies in both directions. If somebody else prefers thermodynamic to stat mech, I'm not allowed to look at them and say that's wrong. I can simply say, that's interesting. I don't like avocados and you do. That's sort of my take on it.